Hello and welcome to VitoshAcademy. Today we'll be talking about sliding tile puzzle and we'll be solving this one with Python. So what exactly is a sliding tile puzzle? It is something like this. And you can slide the tiles nicely up to the moment when you get 1, 2, 3. For example, I'll simply show how 1, 2, 3 is achieved. Something like this. Yes. Okay, obviously mine 1, 2, 3 is here, but the idea is that you should make 1, 2, 3 on the upper end. It's not that tough, but it is not as simple as you would probably expect. The thing is that we should be able to solve this one with Python and with DFS, which is depth first search, with A star and with IDA. So this is 1, 2, 3 here, just to show you a bit more. 4, 5, 6 is how you get it like this, and 7, 8 is like that. Okay. Now let's go into Python and see what exactly are we going to do, how are we going to translate it. So this is Jupyter lab, actually not a notebook, and this is how our input looks like. Let's name it input. The first one is 8, which means how many tiles we would be having covered by numbers, and as you see it's actually 9, but we don't count the 0, so this is okay. Additionally, -1 in our case would be the position of the 0, but in our case we have a default position, which is this one. If we write -1, otherwise we have a general position starting from 0. If it was a 0 here, for example, we would have had a 0 there, and then 1 here, and it would have been a bit more complicated to explain. The expectation is to have this as a start, and then to have the moves, for example, left like this, 1, 2, 3, 4, 5. Obviously, the one from the 0 is moved. This is the one from the 0 is the only one. We can move to the left. So left means 1 to the 0, and another left is actually fixing it. It won't be that easy, actually. It will be a bit more tough. The tests would be including also 3 by 3, 4 by 4, 5 by 5. And I think this would be enough. And let's start with the more interesting code. We would be using some coordinate helpers. I'll just delete this, as they're not that useful. These are our coordinate helpers. Position, row, column, and position index. They look like this. So what each one of these does, let's bring our friend Excel here, and I have prepared a bit more here, and I'll explain immediately. So these are ways to get the coordinates. For example, position, row, column 5, 3 would mean that n is 3 in our case here, and in a 3 by 3 sliding puzzle, the 5th element is on position 1, 2, which means row 1, column 1, which is understandable and somehow obvious. And position index would mean a bit more interesting thing. Position index means that in row 2, column 0, so row 2 is this one here, column 0 is this one, we would be having the 6th one as an index. For example, row 2, column 1 should give us a 7. Let's try this one. Row 2, column 1 in 3 by 3. Okay, it's still giving us a 7. Correct. So finally, let's start doing a bit more interesting thing. What would it be? Let's start parsing the puzzle, pretty much the input that I have just deleted, I'll rewrite it, and building the goal. Puzzle parsing is of course a function. It looks like this, and it accepts pretty much a text, because this is how our input looks like. Yeah, not bad actually, it works. So we'll keep it this way, although we could have used here automatic assigning. This is n, this is the position index, and then for each row of the index we could have read it this way, but it will also work like this. Of course, not on a judge system, but in general it will work. Let's see what we get. N is the number of tiles. Pretty much. So in our case it would be 8. And for 8 number of tiles, we should make sure that the total is number of total tiles, which would be numbered plus empty one. I here would be the index position, or with otherwise the go index, where 0 must be placed. Yeah, -1 means bottom right. -1 is default for bottom left. Okay. Of course, we make a check whether the input is okay. And by okay, we mean if it is 8, then 8 plus 1 is a square, and we are asserting that it is okay. Then we print the board, and then we explain what we have done. Then at the end we have a goal. The goal is really simple thing. It should be the board as we are expecting it. Let's activate this. And now try the demo text. As you have seen, I have already tried it before, but let me here explain. So it is N and I here. Well, the first N is the number of tiles. Then we have the small n, which is 3 by 3 in index positions, and I here is the number of rows and columns. Okay, this is how it looks with the default one having the 0 here. And this is our goal. Just to explain what I mean before, let's put this one, instead of 8, let's write 7. And we are expecting an error, of course. We have an assertion error here, pretty much here, n by n is not equal to total. And this is quite good. So let's keep it with 8 and continue slowly with the next one, pretty much explaining Manhattan heuristic. So let's present the code first, and then I'm going to discuss it as well. So these are the two new functions: destination row common for tile and Manhattan heuristic. So what do these do actually? So for each numbered t, we are looking for its go square, which is go row, go column, so to say, or in our case, row and column, or go row, go column, given the index. Then we add row minus go row plus column minus go column. Of course, in absolute values, we're ignoring the blank, and this is our Manhattan heuristics here, as you see. And what can we do? Pretty much, let's see, the goal destination for tile 8 here would be pretty much destination for tile. We write the 8, we write the n and the I, and in our case it returns 2, 1. What does this 2, 1 actually mean? Let's take a look at Excel, and I'll try to explain it here. So we are pretty much saying in a perfect case where our 8 should be living, and in our case it is on the second row of the first column, which is here. Let's try with 1, and I'm expecting 2 zeros. Yes, 2 should be 0, 1, and so on. For example, 5, which is in the center of the perfect solution, starting like 1, 2, 3, 4, 5. 5 should return 2 1s, standing for 1 row, 1 column. And this is quite okay. Why is this heuristic good? It is admissible because it never overestimates the true number of moves. Never ever. This is pretty much the Manhattan. Each move changes tau in Manhattan by most 1, and the heuristic is also consistent. It satisfies triangle inequality, smooth search, no reopens needed for ADA star. If you remember what ADA is, it's Iterative Deepening A star. And this heuristic is okay and acceptable. Let's try with the solvability test now, and let's write it down, because not everything is solvable. About half of random 8 puzzles are only solvable. Without this check, your search might run forever, and this is not the best thing to do. So let's give it a try. Now let's talk about the solvability. Here we have defined 1, 2, 3 functions, inversions, parity, row from bottom, and is solvable. Pretty much, what is the main idea here? The main idea is that we can find out whether n by n puzzle is solvable only if we count the inversions, and the inversions in the goal and in the given puzzle are with the same parity. Okay, I'm pretty sure this doesn't mean anything to anyone who hasn't done anything with puzzles, and if you have done anything with puzzles, you wouldn't understand what I mean. So let's give it a try. We have something that I have named unsolvable 3 by 3, and we have 2.21. This is one inversion, and then we have 8.7. This is a second inversion, and we can say whether it's solvable, and we can say that it is solvable because we have a parity of the inversions. Here we have 1, and 8.7 is the second one. In order to make this one, of course, what we do is we are flattening the whole thing, and we find out, so to say. Yeah, so if I change the inversions, because they are currently even, if I change them to odd, they would look like this, and they will become unsolvable immediately. Why? Because here we have unsolvable, and in the result we have a solvable one. So you see, it immediately we have a false. Okay, we change the inversions once more, for example 6.5, and it would be true. We change them also one more, let's say this 2.3, 2.3.2, and then it would be false. So pretty much that's the idea, the whole thing. If the initials are, if the unsolvable is, for example, odd, and the initials is even, then we are not going to be able to solve it. Here it's how it is implemented. Let's continue with the next part. And the next part is pretty much the tiny engine of the IDA solution. It Iterative Deepening A star. So we have the moves are mapped, we have the up, we have down, we have left, and we have right. What is interesting is that up is actually meaning that the tile has gone down. And something else which is also really important is that we should be avoiding immediate backtracking by undoing last move. Pretty much if we say up and we go down, and then we can go up and down like forever without having anything useful for us. The same for down and up, the same for left and right, and the same for right and left. These are the opposite moves for each of our moves, so we should be really avoiding them, as just playing them wouldn't bring us any value. Okay, so this is pretty much the whole tool, the heart of the code, the solving, which returns the tiles of the direction or pretty much none. And yeah, here it says okay. If the result is okay, it's perfect. Otherwise, if it gives infinity, it gives none. How does it work? That's an interesting thing. What is this threshold, for example? Well, it takes the start, the n, and the I from H Manhattan. It runs depth first search for each node, computing f, pretty much forecasted, equals g, which is the goal here, plus h, which is heuristics. So f is forecasted, as I mentioned, g is goal, and heuristic is for heuristic, pretty much. So if f is bigger than the threshold, if the forecasted is bigger than the threshold, return f cut. And if we finish without finding the goal, as I mentioned here, unfortunately, we set the threshold to minimum cut, and then we repeat everything once more. Yeah, these are the best cuts. And we move the blank internally, but we record the tile direction for the input. And pretty sure it looks like a nice implementation of depth first search. So if forecasted is go plus h in our case. And let's see how it works. The function is okay. This is how it looks. And now let's try for something near go. This is our initial thing. And then we'll try to see and to solve it. Let's try go 3 by 3. This is our go 3 by 3. And let's try to solve this one. So it simply says that from the go 3 by 3, we should go twice to 0. And it should be ready. What if we put the 0 somewhere else? Let's give it a try here. Yeah, quite a lot of solutions. What if we do it here? Well, they should be enough. This is how the code looks like. And let's do one more thing. The one more thing would be some kind of presentation. Instead of using this, what we are going to do is we're going to print on each move how our puzzle looks like. Okay, let's write the code. And finally, we are in the last part, direction to blank. This is how it looks. So whenever we have left, it means that the blank has moved left. So actually our move was to the right. Then we have the apply steps, the print board, which is actually interesting, and the replay. So as you see here, for each print, this automatically makes sure that we don't have the whole thing like lines, but we have them 1, 2, 3 and then down. Let's take a look how it looks like. Okay, so this is our demo. Demo is 8 minus 1 here. It means that the 0 is there. If you remember me saying something like 20 minutes ago, then write something in the comments. If it's not minus 1, it means if let's say 1 here on this position, then the 0 should go there. And let's see how this one is going to look. So we started with the demo text here, and after some time we finish with left, right, left, right, left, right, with the 0 on the position that I have mentioned. And if we don't want it there and we want it somewhere on the normal place where you would expect it, let's take the default one. The default one is here. Would it be able to be solved? Let's see. It's 50-50. Sometimes yes, sometimes no. And we see up. Up means the 4 goes up like this. And after the 4 goes up, we have 1, 2, 3, 4, 5, 6. And of course, then left. The left is these two are switching. So the 7 goes to the left on the empty, and another left. And this is how everything goes. Okay, so let's try to recap everything. What have we done so far? We solved the sliding puzzle, which is an interesting thing in Python. Position RC and position index are important. RC is giving us the row column, pretty much meaning that row 5, column 3 has 1, 2. What does it mean? So so RC is not exactly a row column, it returns row column, so it returns this. And the 5th thing here in a 3x3 is actually 1, 2. If the 5th thing on a 4x4 was needed, let's see, 1, 2, 3, 4, 5. So it should be here, and it should have been 1, 0. So let's try. Let's see, or 1, 1. The 5th 1, 2, 3, 4 on 4x4. Okay, n is 4x4. Okay, 1, 1. Okay, so oh yeah, we have the 0th index. Anyway, that's the idea of RC. IX is the index, and this is an important. Then we parse the puzzle, build the goal, and run a quick demo text, just showing how it parsed and how the goal was looking. Then the destination RC and the Manhattan were the next functions that we built. Inversion parity row from bottom is solvable. What needs to be remembered here is that the parity should be the same as in the result, which means the following. Resolved example 3x3 false. Is this unsolvable because we have a lot of inverse parities? For example, here we have 1, then 6, 5 we have a second, and 8, 7 we have a third one, and in the original one we only have an even number. So if we make these ones even as well, then everything works. These are our moves that are pretty much self-explanatory. We should be careful because every time we move, we don't move the 0, we move the thing around the 0. So it's a bit reversed. Avoiding immediate backtracking is really important, like doing left, right, 100 of times wouldn't bring us to anywhere. Then the whole list of tiles directions, or none if they are not solvable, is here's the so-called engine, with of course DFS that was also presented in the previous video. If you're following VitoshAcademy, then this is the one near goal. And this is how it looks like. Now the demo text, looks like this. It's 8 by 8 and -1. Let's use like 15, and let's try to put some numbers here. So after 8 we have 9, we have 10, we have 11, we have 12, we have 13, and we have 14, and of course 15. They should be easy to see. And now let's try with the replay with 15. Should probably take a while, if it is possible at all. I haven't counted it. I'll pause the video for a second. And it took really a lot of minutes, so I didn't wait it for it. What I have done is I have changed a bit just to make sure it wouldn't take so much time. So we have 1, 2, 3, 4, 5, 6, 7, and 8 already pre-declared. Then we have 9, and the rest are a bit random. Okay, 15 is not random, but the other like 5 positions are okay. Yeah, so we press Shift Enter, direction to blank, and we replay. So after 1 down, 1 right, 1 up, talking about here the 0, then 1 right, 1 down, and a few others, we have finished with the correct one. So far so good, everything is okay. So thank you for watching VitoshAcademy so far. Enjoy the rest of your day. If you have any ideas about programming videos, mainly with Python, just write a comment. Or if you have no ideas and you just want to write something nice, just do it. So thanks for watching once more. Enjoy the rest of your day.